Okay, I'll talk to you about a slightly different topic. I'm talking about bottom coal ash, not the fly ash, a different fraction of the ash. And I will be summarizing for you studies that were conducted. I made a calculation with Dr. Inbar a few minutes ago, and we came up with a number of about 25 years. So it's very long, Yossi. Yossi was doing his master degree in my lab when we started to work on coal ash, not with Yossi, somebody else. But it's already 25 or 27 years ago. The rest goes, the last experiment I'm showing to you, it's a kind of a review, has been conducted in 2009, 4 years ago. So that's where we are. We are not working on coal cinder at the moment. What I'm going to show you is the use of bottom coal ash or coal cinder as a component of gross media or container media, which would mean, those of you who do not know, the media which we use in greenhouse production, either in channels, in the soil, or in pots. So as a potting media, basically, growing media, there are different names for this in English. I can use them, I'm maybe using them different names for the same purpose, and as used in English. The two of us are myself and Tzila Aviad. She's my laboratory technician, has been my laboratory technician for at least 30 years. So she's working with me all along until today. Okay, let's go ahead. What is the problem? The main problem that I see, and that's what brought us to work on bottom coal ash, was the fact that we are using as an alternative, or the main source actually being used in Israel in greenhouses is volcanic ash, or tuff as it may be called, scoria in other countries. A material coming from volcanoes, from tails, from big volcanoes that were active in Israel many, many years ago, mostly in the Golan Heights. And this is an example of a big, it's actually a lot bigger than you may consider from what you see. It's a very large Tel Fares in the Golan Heights, and a tremendous amount of material has been taken from there, which in my eyes is a very bad injury to the environment, to the landscape. And maybe one day will happen that Israel will have peace with Syria. I do not want to predict on that. But if that happens, I'm sure that the Syrians will come to us and ask for some compensation for that amount that was taken. The amount of tons taken from this mountain per year is about 150,000 tons. A small fraction goes to greenhouses. I would say about 40 up to 50,000 tons a year go to greenhouses. The other fractions go to many other purposes, gardens, and you name it. And it's a very good material. The effect on the landscape is a different issue. So we came up with the idea, together with Omri and other people, that we may look at bottom coal ash as an alternative to volcanic ash. And the results you will see along my lecture are actually very promising. The commercial success, I'll let Omri talk about it. That's not my field. I'm not counting the tons that are being sold. But the competition with the company that sells the volcanic ash is strong and harsh and not very favorable to coal ash. It's like a struggle between two companies that have different products. Okay, what does the company do? Actually, the coal cinder company, or the company that got the contract to separate it, it's working here in the Ashkelon power plant, electric power plant. That's the main place where they do the separation. They do a separation with machines and come up with material that we basically define for them. What size do we like to have for greenhouses? Here is a pile after this sieving and separation at Ashkelon. This is the material we are interested in. And of course, there is some rejects which go for construction, other purposes. So the product that we eventually are looking at is this product, and this is a technician, Tzila, worked with me. Imri is here, who is marketing the product, and this is Warren Dick from the United States, who was a partner with us on one of the major projects like 4 or 5 years ago, and with whom I cooperate on many other fields as well. Warren Dick, by the way, the chief editor of the American Society of Soil Science, American Society of Agronomy, and Crop Science Society of America. He edits all the journals of these societies, and it's been a pleasure to work with him. The aims of our research: first is chemical and physical characterization of coal cinder from power plants, to know what we have, a little bit from the industry. That's where actually we started. Not as good as a product, not very uniform. But the power plants produce much more uniform product for us. Evaluation of the chemical and physical properties of a bottom coal cinder in light of its potential use as a container medium or growth medium, just mentioned it to you. Evaluation as above for coal cinder mixtures with organic matter, compost, for example. So just if you can see a little bit of the products, the organic composts are a little too dark in this photo. Composted grape mark, composted separated manure, and it could be sewage, sludge, or other products as well. Here is a coal ash or coal cinder, and here is a volcanic ash. So basically what I'm going to show you is a comparison between these two products. Okay, so we did a lot of chemical studies, physical studies. I'll show you just a little bit of it because I know that Yossi is dying to cut me off, right? It's nice for a former, many years ago student to say to the boss, go home. I'll give you the chance, I guess. So electrical conductivity of the products and the number of pore volumes. In other words, we packed the products in columns and leached them and looked at what we have. We are leaching here with a solution. Here is a buffered pH solution, and here is an electrical conductivity solution. You see the line for the electrical conductivity is here, barely seen. This is the pH. So these are the solutions. And now we look at the leachate. What do we see with the leachate? pH. pH is, I'm talking here, by the way, about the volcanic ash. It's not the coal. The pH is maintained at a relatively high value, above 7, 7.3, 7.4, significantly above the pH of the leaching solution. So in other words, the tuff, the volcanic ash, has a buffering capacity, and the pH is not necessarily equilibrating, certainly not rapidly, with the nutrient solution. Now, if we look at the electrical conductivity, there is a leaching in the beginning, a very quick leaching or small pore volume needed, and the electrical conductivity reaches that of the nutrient solution. Not a surprise, you'll see the same, I guess, or a very similar one for the coal ash. Now let's look for the same graph for coal cinder. You see here the pH. Again, it maintains its relatively high value. It does not meet the pH of the nutrient solution. That keeps significantly below, which is not that greatly desired. It's a limitation, but we'll see how the plant responses on this. Electrical conductivity, the coal ash or coal cinder is more salty than volcanic ash, but it loses the salts very rapidly. So again, it's actually not an issue for the farmers. Within half pore volume, that's actually nothing, we reach the value of the nutrient solution. So we can get rid of the salts actually very easily. Now, a few elements that we look at, I think we'll look at phosphorus and potassium only. Here are the levels. These two are the levels in the nutrient solution of the nutrients, and here are the levels that we find in the leachates. Let's look first at phosphorus. Again, by the way, I forget to say, the volcanic ash, it's important to know. Volcanic ash, phosphorus is maintained at a low level for quite a few pore volumes, and only after 4 or 5 pore volumes, it starts to raise or maintain a more or less constant level, which would mean that in the early days of using growing plants on this, one needs to supply the nutrients. They are not there, they are disappearing. Same is true for potassium. You see here, again, very low, and only slowly later it starts to raise. The different mechanisms, potassium would be absorbed, and phosphorus mostly precipitated as calcium phosphate. But the farmer or whoever is going to grow on these media needs to compensate for that period to make sure the plants will not be harmed at the early period. Similar results, somewhat different, but giving you the same kind of concept. Leaching coal cinder, here is the potassium, the blue line here, and this is the level at the nutrient solution. Here we're talking about milligrams per liter, ppms. So slowly reaching the level similar to that of the nutrient solution. Phosphorus, the same story. In the beginning, low, and takes a bit of pore volumes. You can use the word time of irrigation until it reaches reasonable levels. Again, it would mean that growing plants in there one has to take care. Now, what we did a lot, we investigated a lot the mixtures. What I was showing until now was pure mineral components. Now I'm adding an organic matter to buffer or compensate many properties, both physical and chemical properties. So just look here at the study. A study on the absorption of phosphorus by media without, you see this for example, for tuff, volcanic ash, absorption of phosphorus from the solution, different concentrations in the solution. So phosphorus being disappearing from the solution or adsorbed. However, when organic matter is being added, these are at 2 pHs, I'm not going into the details, but as soon as organic matter is added to the system, the absorption of phosphorus or removal of phosphorus from the solution stops. So the organic matter buffers compensate for that. The same is true for the coal cinder. Look at this one, 2 pHs, this is pH 8, pH 6. There is significant absorption. However, with the addition of organic matter, it flattens out, no more absorption, which means that it's a good buffer for the system. You can add the organic matter and then forget about all this disappearance or lack of phosphorus or potassium, which I was showing you before. Okay, now I was talking about chemical properties in brief. Now I want to talk a bit about the physical properties, which are very, very important in container media. They're actually more important than the nutrients, because nutrients are relatively easy to supply. However, the appropriate ratio of water to air is very difficult to provide, and it's not so easily made. So I want to show you how we do it. We make a retention curve where on this side we increase the tension, we increase the suction actually, and on this axis we see actually the water content based on volumetric water content. So you see that as the tension increases or the suction increases, we lose water from the system, and every cubic centimeter of water that is being removed is being replaced by air, of course. That would tell you, so the difference from here to, let's say, the curve here, from this point to this point, will tell you how much air has been formed or has been taking place in this system. So we look at the data. Now, the blue one, matsait, and compost, is the volcanic ash. That was a commercial name given to the material by the company. Volcanic ash with compost and the commercial substrate. So the commercial substrate is running here, and these two are running here. What one can see, and I'll show you that with the numbers, the volcanic ash, even with the compost, is losing water very rapidly, and there's more space for air being formed, which is on one way good, but if it's too extreme, then the plants are subjected to a lack of water. So one has to find the appropriate balance. I wrote down here, the ideal substrate would have 20 to 30% air at a level of 10 millibars, a suction of 10 millibars. And we can see that actually the matsait, this is the coal ash, is very well within the range. Volcanic ash is slightly above. And then we look at easily available water, and we look at water buffering capacity. All parameters important. We can see that the volcanic ash and the coal ash are both fitting reasonably well, and they actually create a substrate that is good for plants, and we'll see it from a large number of plant experiments that I'll show you. Another issue we wanted to study is stability of the grains. Are the coal ash grains stable sufficiently as the volcanic ash is? Because degradation, physical breakdown, will cause a very big problem to the grower. So we wanted to see how stable they are. We leached the material in columns. You see here the particle size distribution for the volcanic ash. The tuff is here, before and after leaching. Before is the blue, and the more purple type is after leaching. And there is a slight change. I wouldn't even call it a change. It's stable. The volcanic ash is stable. If you look at the coal, very stable, and also has a much nicer particle size distribution. It's much more on a normal type of distribution, rather than the volcanic ash that has all kinds of humps and jumps in the curve. So that kind of very normal type, Gaussian type of distribution of particles is highly desired. And the second conclusion, the particles are stable. They are not degraded. How many minutes? 1.5? 10 minutes. Oh, you're not too bad. What is the other issue we had to look at is the trace element concentration, toxic trace elements and also radionuclides, which we had to check. And I'll show you that very briefly. Here are all the materials, and I have coal ash and volcanic ash. The volcanic ash is in blue, purple for the coal. You see that the distribution is fairly similar, and I also can say, as a general statement, there's not one element that would cause a concern. Not in the volcanic ash and neither in the coal cinder. So we are in good shape on that. We looked also at trace element concentrations, both in the leachates. I'll not talk about that. They are very low. In generally, always much better than drinking water standards. So if you have a leachate in the bottom of a pot, you grow plants in coal cinder or volcanic ash, and the water is better than drinking water standards, I would say there's nothing to worry about in this respect. So we looked also at the fruit in the plants and look at the two materials, both with compost, volcanic ash and coal ash. The numbers are very, very similar. They're not necessarily identical, but the differences are small. So what I'm actually saying here, since volcanic ash is so widely used in the country, no limitations, no trouble with the Ministry of Health and no trouble with the Ministry of Environmental Quality, we should expect the same attitude to coal ash. But we had much more trouble in bringing it into the market. Our material, not mine, it's Omri's material, had to continue and struggle with the ministries to prove that it's okay, whereas volcanic ash is used freely. Why? One comes from nature. The other material comes not from nature, originally from nature, of course, but then later on being burned. And we had a lot of trouble, but most of the time we were successful in the struggle. Although they forced us to prove that we are in this situation with each individual crop where we wanted to use it. To show it for this crop and tomorrow for avocado, then to mango. It's a tremendous headache. And on the other hand, there is this 100,000 tons per year going to the field, nobody asks any question. That's bureaucracy, as you know. I don't know if you have your people from the ministry, but I will be very happy to even argue with them. Trace element concentration in melon fruits, another type of fruit or vegetable, as you wished. And again, the numbers are practically similar, not identical. For example, molybdenum here is 0.6 in coal ash, and for the volcanic ash it's significantly higher, 50% more. But that's no problem. Volcanic ash is approved. Now Omri has to show that coal ash is also good. Radionuclides, I would say just some general statements. The aim was to measure radionuclide levels in produce grown on coal ash or volcanic ash and compare it to health standards. We looked at these elements, radionuclides. We did it in places which are permitted to do it, not us, of course. The results, no significant difference was found between radionuclides concentration between produce grown on volcanic ash and coal ash. And conclusion, coal and volcanic ash are safe container media to use for crop production, including edible crops. Now, a little bit to the plant side, I'll show you quickly. This I'll go quickly. A number of crops, how we grow them, and what the results are. This is a standard peat mix coming from Holland, by the way, bought from Holland, which are the godfathers of container media. Coarse cinder, look at the plants. These are croton plants. Cinder plus compost, different. This was coarse and this was regular. And the volcanic ash, and I would say the coal cinder performed beautifully, very well in all of these. Yossi, you were the photographer? Maybe. Okay, gerberas in the field in a very, very nice way of growing. It was in a farmer's field. This is a pot with container with coal ash in the bottom with compost, and the plants grew extremely well. I skipped one. Cabbage in pot plants. Again, the results are promising. This is a matzait alone, tooth alone. As soon as you add the organic compost to the system, there is a yield increase. And this is Ripodid, another type of container medium from coal cinder. You see the results are good, the growth is good, and organic matter does have a very strong positive effect. The same is true for basil, same type of graph, so I'll go quickly. Carnation yield, we have actually two sets of graphs, and I think one axis is probably missing. The green one shows you the total weight of cutting, so let's look at that. Cinder plus compost, coarse cinder plus compost, and volcanic ash plus compost, all performing well and the same. Yossi, you made very nice signs. No, not you. Okay. Now melon grows. Look at sand. This is a typical medium in the Arava, in the whole southern part of Israel. They do it in the original soil, which is sandy. This is the yield they got there. I have here separation by quality of the food, but let's just look at the top. Once we add compost to the sand, completely different type of results. Volcanic ash alone, again, poor, but volcanic ash with compost, beautiful shape. Coal ash with peat, good. And the same is true for coal ash with compost. In this experiment actually performed as good as the sand plus compost. In other words, very satisfactory. Look at, these are tomatoes grown in the Jordan Valley. One of the farmers who agreed to take it. This is year number 8 on the same medium, because one of the criticisms is always, how long can you grow on your medium, how toxic it will be to plants. This is year number 8, no decrease in yield, by the way. The farmer was very happy with it. I think he still has a field. Does he? I haven't followed him for a while. Yields compared here, volcanic ash plus compost, coal ash plus compost. You see they go together. This is pepper plants in the Arava. You see them being planted in a kind of like a channel in the soil, where they add soil and regular soil. They add coal cinder and in addition, the compost that I mentioned. Look at the field, looks happy and well. There are pepper plants at Tzofar, grown by Tzofar farmers. By the way, it's on the Jordanian side of the border, according to the peace agreement with Jordan. So we had to cross the border to find 2 sleeping Jordanian soldiers at the border crossing. They didn't even look at us. Anyway, this is in the local soil, and this is in the coal cinder with compost. You see coal cinder, 20% compost. I don't have to convince you that they go a lot better here than here. Protea plants is in Shar HaMakim, where Imri comes from. You see soil and you see the coal ash, by far better, and I'll go very quickly here. Different types of plants growing in container media with coal cinder, and they're doing well. And the last experiment, which we did in 2009, we planted oak trees that had to be transferred from one place because of road construction to another site. So these were planted either in a soil, regular soil, or in coal cinder with compost, like you see here. The table is still a residue from a Hebrew lecture, but they did really well. And you see here, this is a coal cinder with compost, and we're talking here about the growth height to which growth it grew compared to a control. And then we have growth to the sides, and it's significantly better in these plants grown in the coal cinder than in the soil. So they do well, and I heard that they are still doing well 4 years later. And if you look at the roots, for example, we also did that. These are roots in a mixture of the coal cinder with compost. Quite a lot of roots. This is not quantitative, but you can look at it and obtain an impression. This is a soil. This is a coal cinder, and you see that the soil lacks roots, whereas the cinder has them. Yossi, I'm coming to a summary conclusion for your happiness. So a chemical analysis, the pH of the leachate ranges from 7 to 8. I'm talking about the coal cinder. Levels of potentially toxic elements, including boron, which can be very toxic to my friend from Greece. Boron at a very light increase can become totally toxic. You have to be very careful. They are low, below critical levels, no problem. Excessive salts are easily leachable, no significant problem. P is removed from the solution, and therefore the farmer has to take action, either add more fertilizer or mix the medium with phosphorus. Physical analysis, no degradation during growth, a lengthy growth period. Actually, I showed you a long leaching period. Water retention curves exhibit low water holding capacity. It can be, however, be enhanced by compost addition and become ideal, actually. And this is the last. Compost addition also results in enhanced plant growth, significantly enhanced, improved buffer capacity, suppressiveness to soil-borne diseases. I did not talk about it, but it's a major advantage. And the recommended level of compost addition is about 25 to 40. 25 we found is sufficient. Plant growth experiments in commercial and experimental greenhouses show that mixture of coal cinder with compost supports plant productivity at least to the level obtained in volcanic ash growth media, again, mixture with organic matter. So the both are comparable, and I wish to thank you on behalf of me and Sila.
Thank you very much. No time for questions.